Nuclear magnetic resonance spectroscopy, or NMR for short, works by manipulating a property possessed by subatomic particles called spin. You'll have heard all about electrons having spin before, and that these electrons fill energy levels in the atom according to their spin. Materials can show various types of magnetic behavior according to how the electrons are arranged. For example, materials will be attracted to magnets when they have unpaired electrons. It turns out that nucleons, particles in the nucleus, also have the property of spin. They too can behave like tiny magnets if there's an uneven number of them. Normal hydrogen atoms, for example, have only one particle in the nucleus, a proton, so these will be able to interact with a magnetic field. Let's have a look at how NMR gets information about these atoms. Imagine an atom as a tiny magnet. A regular magnet in a compass will spin to align itself with the Earth's magnetic field, but that doesn't mean that we can't play with it. If we supply some energy, from a finger pushing for example, then we can turn the compass away from north. The compass now has a higher magnetic potential energy, a bit like pushing a ball up a hill to give it more gravitational potential energy. Once you let the compass go, that energy is released to the environment through movement and heating. We can talk of the magnet as being in two states: the relaxed lower energy state, where it's aligned with the Earth's magnetic field, and an excited state, where it's opposing the Earth's magnetic field. We can play with the situation still more by adding a stronger magnet. This has the effect of increasing the energy required to move the compass, and increasing the energy that is released when the magnet flips back into alignment with the applied magnetic field. This explains why NMR machines are usually so big. They contain supermagnets, which need both a lot of cooling and a lot of shielding when operating. A sample is placed into the magnet, and the atoms align with their spins with a strong magnetic field around them. Next in the machine comes the nudge. We want to get the spins of the nuclei to oppose the applied field. Obviously, this isn't something that we can do with a finger, but it turns out radio waves have the right kind of energies to help us get this to happen. All of the spins in the atoms of our molecule flip, having been excited by the radio waves, and when the radio waves stop, the nuclei release energy back to the environment that we can measure. It's a bit like listening to a molecule sing. Here's a molecule that gets its spectrum taken a lot. It's called tetramethylsilane, or TMS for short, and it's important to realize that the nuclei of the atoms we're measuring are in atoms, and therefore surrounded by other particles with magnetic properties too, electrons. These electrons act to shield the nucleus from the full effect of the field. More electrons generally means more shielding and therefore less exposure to the field. And that means that any atoms with different electron densities around them will release radio waves at slightly different frequencies. These frequencies are characteristic of the types of atoms and functional groups around them. Atoms which have neighboring groups containing highly electronegative atoms often appear more to the left or downfield from the tetramethylsilane peak, which is used to calibrate a zero value for the spectrum. Of course, if you look carefully, there are a few here that don't quite seem to match or follow this pattern. You won't need to memorize all these values. You'll always be provided with the data you need, you just need to interpret it. Let's have a look at the spectrum for 1-bromopropane. This spectrum has 3 peaks, other than the TMS peak on the right. That TMS peak allows us to calibrate a zero value for the spectrum, and everything else is measured against it. The most downfield peak is due to the hydrogens attached to the carbon with the bromine on it. Both of them generate one signal because they have the same connections to the rest of the molecule, and therefore will be experiencing the same levels of nuclear shielding. We say that these 2 protons are in the same environment. There are 2 other hydrogen environments in this molecule. Firstly, there's the CH2 group. You can see it's been shifted a little bit from where we would expect to see it if it were just in an alkane, but the general area is the same. And then lastly, there's the environment with the hydrogens in the terminal CH3. Notice that the TMS peak has only one peak. By looking back at its structure and thinking about the environments of the hydrogens within it, can you work out why there's only one peak? We can also plot an integration trace for the spectrum. It turns out that the area under each peak is proportional to the number of hydrogens in that environment. More protons, greater area under the peak. You can measure the height of the integration trace and compare. In our molecule, the ratios of the peak are 3 to 2 to 2, because there are 3 hydrogens in one environment and 2 in the others. Note that we only get a ratio here, so for example, a 1 to 2 peak ratio could be representing 2 and 4 hydrogens respectively. Here's one to think about. This molecule has 12 hydrogens. Why are there only 3 peaks? Can you match the peaks to their positions in the molecule using the data in the table? And can you determine the ratio of the peaks from the integration trace and use this to confirm which peak matches with which hydrogens? If you'd like to play with some more examples, you can check out the RSC's Spectra School website.